So far we have seen what is an SHM and how to represent it as a projection of a rotating vector. This rotating vector is called a phasor, and phasors are a very powerful technique of combining SHMs. We will be using phasors to combine two SHMs of slightly different frequencies and get an interesting phenomenon called as beats. So here is our first SHM, and this is its equation of motion. Y is equal to 12 sine phi omega t. Its phasor looks like this, and if you look at it step by step, then you will realize how the motion is following the phasor. Phasor goes down, the particle goes down, the phasor goes up, particle goes up, and so on. So this is how a phasor governs the motion. Now let us look at its displacement against time graph. It will look like this. So as the particle moves, the displacement against time graph is a pure sine wave. Now let us look at the second SHM. If we watch them, then we do see some difference, and the equations of motion also tell us that their frequencies are different. But other than that, describing that difference or understanding that difference is difficult. If we watch the two phasors, then maybe it is little easier. So we can see to start with, the two particles are in opposite phase. The phasors are pointing in opposite directions. Then as the motions continue, you will see the red phasor is rotating faster, and that is because its frequency is higher, and eventually it will catch up with the other phasor and they will be aligned with each other. Because of the frequency difference, again the red one will rotate faster and eventually it will be in opposite phase. So this keeps happening periodically. The two phasors get aligned and opposed, periodically. Let us now watch the resultant of these two phasors. This will be the effect of superposing these two SHMs. This could happen when, say, two sound waves are traveling through the same medium, or they are passing through a point. Then the particle of air or the medium at that point would be acted upon by two SHMs, one because of each sound wave. And if the two sound waves differ in frequency like this, then the displacement of that particle will be governed by these two phasors, or rather the resultant of these two phasors. So let us watch this resultant. We'll watch it step by step. So here we have two SHMs, one represented by the red phasor, the other with this blue phasor, and this green phasor is their resultant. So that is going to decide how far the particle will be displaced at any point of time. As the time progresses, you will see the angle between the two phasors is reducing, so they are getting aligned, and you will see that the resultant is also growing, and it has reached a maximum value because the two phasors have aligned themselves perfectly. And then because of their differing frequencies, they again part ways, and slowly they are going to go in a opposing phase. So here they are almost opposite to each other, and the resultant has vanished. So the particle will have the minimum amplitude at this point of time, and this will keep on happening. So let us give this resultant to a particle and see how it moves. So you will see this particle is also oscillating up and down, but there is a difference. It is not a simple oscillation. It's an oscillation whose amplitude is continuously varying. So right now it is maximum, it is dying down to a minimum now, again it is building up to a maximum, and so on. So if these two were sound waves of equal loudness, then the result would be, at this location, we will continuously get a sound which is slowly building in amplitude or loudness. Then it will die down to a perfect silence. Again it will build to a loud sound, and this will keep on happening periodically. Let us plot its displacement against time graph. So for this particle here, and you will see it more clearly how the amplitude increases, again dies down, again it builds up to a maximum and dies to a minimum. This maximum amplitude is called waxing, where we hear a loud noise, and the minimum is called a waning, where it reduces to a silence. This phenomenon is called as beats, and the frequency of these beats is equal to the difference of the frequencies of the two SHMs or the two waves that are causing this SHM.